When I got wrong, the first thing was the only thing that I really messed up on. That's the thing I was like, are you doing this? Yeah. I want to angle about that. When you got water cancer, I was just an add, it was like 180. Yeah, like that there. I guess maybe there's something happening.
You found that area and then I messed up like that. He messed up. Yeah. It was so funny. I see this one and it came back here. What happened to everybody? Why is there nobody here? Well, you guys aren't nobody. Where? Micrometers is to the -6, right?
Micro 10 to the -6.
1/8%.
Yeah. We don't think clearly on tests. SI unit of mass. Kilogram, yes. You have to make sure you had that one.
The train, number 2, the train. You had to do all 3 parts and figure out the total displacement in kilometers and the total time in hours. And there was enough tricks there to watch out for. The acceleration was given in hours, kilometers per hour squared. You had to watch out for all of that.
I mean, I know it's kind of like some wrong, but those stupid. I don't like it a lot. There's much any of this was an app, but it was yours. Like, look first.
So yeah, the train number 2, you had to break it down into 3 parts. Were there any questions about 1 or 2 that you were not sure about?
I had a question.
On 1 or 2?
Neither.
Okay, neither. Which one?
On number 6.
Well, we're going to get through them.
Oh,
So you want to just hold off on that one?
For number 2, we don't have the right hours. So it's at A and B. Like it says overtime and S3.
Process.
Yeah.
In hours.
Yeah, I wrote 10 hours. No, I wrote hours per each one. Is it wrong or you cross it out?
I don't know. I'll have to take a look at what I wrote, what you wrote. We'll talk about it afterwards. John, right? So there was something like 1.6 hours. And the total distance was, I forget, something like 131 kilometers or something like that. 112, 113, I don't remember. Anyway, there's 3 parts and you had to figure it all out. Moving on to number 3, the object. A has a constant velocity, B is object is at rest. Object A crosses B at t equals 0, B accelerates. How long does it take? So you had to set up 2 equations, one for the position of object A, the other position of object B. They end up meeting each other at some point. You solve for the time. And you should have gotten 28 seconds. So far in 1, 2, and 3, 1 you've got a really basic units issues. Number 2 you've got the multi-part problem, and number 3 you've got the 2-object problem. Just following straight to what we talked about. Number 4, or do you left over any questions on number 3? Number 4, we got a rock projected upward from the surface of the moon at t equals 0. It's a one-dimensional motion, constant acceleration. We'll give you the acceleration due to gravity at the surface of the moon. Calculate the average velocity of the rock during the first 22 seconds of flight. Couple of ways to get there. Because it's constant acceleration, you have a couple of choices. But the most straightforward one is to calculate the change in position and divide it by time. Delta x divided by delta t. That always works because that is the definition of average velocity. However, some of you like to be more creative and you went with the v initial plus the v at 22 seconds later, and then you added them and you divided by 2. And that does work also. They get you the same answer. Either way was fair. So what was the average velocity? I don't have it calculated with me.
That was 12.1.
12.18 sounds about right. And normally I would have posted solutions, but my computer went through a Microsoft upgrade, which took it down, which I guess is technically a Microsoft downgrade. Anyway, it's, I don't think I lost any of the files, but I just don't have access to my computer. The IT guys are still working on it. So normally I post solutions. Okay, number 5, you got the position of an object specified as a function of t. You recognize that we have non-constant acceleration. Okay, so that's such a function of t. And I ask you to calculate in number 5. What are we calculating? We're calculating average the position, right? Or the displacement. Okay, the displacement between 12 and 18 seconds. I think almost nobody had any difficulty with the displacement. A little painful, but at least you know what to do. Average velocity, average acceleration. You have to calculate delta V and divide by delta T. It's the only way to get there. For number 5. So V at 18 minus V at 12 divided by the 6 seconds. Non-constant acceleration. Questions on 5, 4, 4 or 5, 3, 4, or 5 before we leave that page?
What's the answer for acceleration average? For the average facility?
I don't remember off the top of my head. 12.4. That was 12.41? Okay.
Thank you.
Okay, number 6. You got a car A with the velocity relative to the Earth and car B with the velocity relative to A. Given its vectors. Now you need to figure out what the velocity of car B is relative to the Earth. So hopefully you simply set up the equation, did your vector algebra stuff, and then you found the magnitude and direction. Magnitude being the magnitude, what is the velocity? Direction specified as a number, some number of degrees from something. That would be a direction.
Okay, so when I did that, I just didn't know which quadrant it was in, so whether I was supposed to add something or not. Is that why I got it wrong? Or, I mean, the answer that I got was, I think 60.
Well, the velocity tells you what quadrant it's in. Because you have the vectors, and at least measuring from the standard positive x-axis, I think it was in the 3rd quadrant.
Okay.
Now, you could have said that you were measuring it relative to the negative x-axis, which your answer might have been fine. But you got to communicate that if you want to use non-standard coordinate systems. Okay, number 7, the mass fired up at an angle of 235. With an initial 35 degrees at 560 meters per second. The mass lands at an elevation 500 meters above where it was fired. It's actually a bad question because there's 2 answers. There's one on the way up and one on the way down. I didn't care which one you specified. Most people picked the one on the way down. But a couple of people went for the, about 2 of you said there are 2 answers. Here's both of them, which is the best thing you could possibly do. Some of you just picked the first one, which is fine. So you had to figure it out whichever way of solving those equations. Find the projectile in air and the horizontal displacement. Okay, number 8. The dot product was a major problem. A dot B, the result is not a vector. So you found your A dot B and you multiplied 8 times 6. Actually, I'm going to write this one down. That one was such a big problem. Okay. Number 8. I hat plus 13j hat. E minus 6 minus 5.
I know that cost me.
All right, so A dot B. It's 8 times negative 6 plus 13 times negative 5. And there is no vector there. It is just a number at that point. What number is that? 6. So we get negative 113. That's your dot product of A dot B, not a vector. And then, of course, you have this other relationship which I wanted you to know. It is A times B, the magnitude of each one of those two, times the cosine of the angle between them. It's just a rather important relationship that ends up getting used over and over and over again. Okay, let's see, so when we did that, we found out that the magnitude of A was, let's see if I can find someone who had the right answers. Looks like the magnitude of A is 15.26. 15.3, sure. Magnitude of B, 7.81. So therefore we get the cosine of theta being minus 113 divided by 119.2 roughly. Or theta is something like 161 degrees. That number will always be between 0 and 180 in the dot product. Angle between two vectors. This is the best way to get the angle between any two vectors. Here's your A, here's your B. Theta. There are two angles between any two vectors, right? There's also the other angle. But the definition of this dot product AB cosine theta is the smaller of the two angles, which means it will always be less than 180 degrees. Okay, and then we got on to page 9, the graph. And one nod to kind of a trick question here. Number 9, I gave you the graph. Using the graph of the velocity versus time, determine the displacement during the first 40 seconds. And important to explain exactly how you did that. Yeah, there was a lot of variations there. So you got V versus T. It's not position. Some of you started talking right away about how its position is increasing in time. Various strange things. There's two obvious ways to get there. One of them is to say that because you've had a little bit of calculus and you know it's the area under the curve, and many of you just said, it's the area under this curve, I'll calculate that. Either from calculus or from triangles. They gave you something really nice to work with. That works absolutely perfect. That's what I was hoping for, really. A couple of the others also said, well, this is the velocity, the slope is acceleration. That slope is different acceleration. So this is just motion with two different constants acceleration. Treat each one as a separate part. Do this part and that part. We were only interested up to there. And there you go. Some of you just got so excited you calculated the whole thing. And anyway, the total displacement, the total delta x, when you add it all up, was 1,200 meters. So if you have any questions, concerns, we'll talk afterwards. if you want to ask me questions afterwards, Rod? Number 5? The average acceleration, you have to calculate it from delta V divided by delta T, because it's non-constant acceleration. So if you calculated the two velocities and then divided by the difference, and then you divide by the time interval, you got it. All right, onward. So you remember something about friction? Back to where we were before we took that little, before Thursday. Let's just see if we can remember what's going on where we have our inclined plane. Here we have our mass, 10 kilograms, nice big mass. 60 degrees. Even though it's 60 degrees, I draw it small. That way I never mess it up. I suggest that you always draw small angles. Otherwise you'll confuse yourself. Especially if they give you an angle like 45 degrees, where the sines and cosines will totally confuse you. So anyway, this thing is moving. So we have a V initial of 1 meter per second. We have a coefficient of kinetic friction being 0.2. And it's starting a distance from the end of the incline of 3 meters. And all I want you to do is tell me the velocity when it gets to the bottom. The speed of the speed of the object when it gets to the bottom of the incline. We'll do the speed and the time. See if you can find a way to calculate how long it will take to get down there. And mass is 10 kilograms. Ariel or Jonathan? Adrian? Edwin William? Ariel, Jonathan, Alexandra. Right. Okay, since we have an acceleration down the plane, we want to work in a coordinate system parallel to the plane. It's the optimal one to work in. You can work in any one you like. Some are easier than others. This is probably the most easy one. So we've got our normal force and our gravitational force and our frictional force opposing the motion. In this case, we know the object is moving. We know which way it's moving. So that certainly helps a whole lot. So the normal force is written in the j-hat direction. The gravitational force, positive mg sine theta I hat, negative mg cosine theta j hat. That is coming from breaking this thing up into two pieces. There's my negative j hat. Here's my positive I hat. And yes, this angle is 60 degrees, and it is not accurately represented in that diagram, but that will help you getting those sines and cosines correct. Because at this point, it's relatively obvious there's a small angle there, that angle is equal to that angle. It's sort of a trick to help you never get mixed up on those sines and cosines. So we're dealing with kinetic friction as our kinetic friction vector in this coordinate system is the kinetic friction magnitude, negative I hat in that coordinate system, minus mu k Fn. So we have to figure out what Fn is. First thing to do there is to sum the coordinates in the j-hat direction. So you get Fn minus mg cosine theta. And this is equal to MAY, and we're going to set AY equal to 0 because we assume that the mass does not move perpendicular to the plane. And therefore we end up with our expression for Fn equaling mg cosine theta. Now I can sum the forces in the I-hat direction. So I would get mg sine theta minus mu k Fn is equal to max. We've got an m in every term, so I can divide by m. It's not 0. And that gets us our acceleration. The acceleration down the plane is g sine theta minus mu k g cosine theta. Let's pop in the numbers and see what we get. 9.8. Sine of 60 minus 0.2 cosine of 60. If I typed it in correctly, I get 7.5. meters per second squared down the plane. Thank you. Time to reach the bottom and speed at the bottom. V0 plus AT would be one way to get there. Acceleration is constant. We don't have time, so that equation doesn't jump out at us being as useful. But the other one is v squared is equal to v0 squared plus 2a delta x. We know how far it's going down the plane. That's the more useful equation. V squared is equal to 1 squared plus 2 times 7.5 times 3 I get 6.78 meters per second. Now it's easy enough to get the time. And I get 0.771 seconds. Questions? Seems straightforward enough? Okay. Similar but different. Five kilogram mass, moving with an initial velocity of, let's say, 6 meters per second in that direction. Encounters an incline at, say, 50 degrees. There's no friction on this part. U equals 0, static and kinetic. But the incline has some friction, and we're just going to deal with the kinetic part. Coefficient of kinetic friction on the incline, 0.1. Our first question, how far up the incline does it go? And then it's going to stop, and we'll assume that there's no static friction for this particular problem, and it's going to turn around and come back down. Well, just on the incline. Yeah. How far up the incline does it go? So obviously there's a bit of how this thing makes a nice gentle transition from that to, we're not going into those kind of details. Does it actually physically work to really try to construct it? But as far as an idea of these calculations, how far up the incline does it go? You have to deal with friction here, so it's not going to go as far as it would if there was no friction. And then when it comes back down the incline and gets back down here, just assume that it stops and we don't deal with static friction, it just turns around and comes back. When it gets to the bottom again, how fast does it go? So it goes up, comes to a stop, turns around and comes back. And we want it V final. So first, let's see if we can get that number, and our ultimate goal Well, the whole practice went very similar to what we had before. Hopefully that seems familiar, just because we just did it. But this time the friction is going down the plane. Why is the friction pointing down the plane? Because the mass is moving up the plane. Friction is always opposite to motion. So from that acceleration, now that we got our acceleration, that is 9.8 sine of 50 degrees plus, what did I say, 0.1 cosine 50 degrees. Yeah, we got 0.1. AX is 8.137 down the plane. That's in meters per second squared. My units. All right, now that we have the acceleration and our acceleration is constant, we can employ our constant acceleration equations just as we normally do. How do we find how far it went up the incline? Find where it is when v equals 0. So 0 is equal to v naught plus at is one way to get there. There are others. We started off with 6 meters per second up the plane plus, not quite. It's actually a negative 6 meters per second up the plane. So our initial velocity vector is in the negative I-hat direction. We have to attend to that and be a little bit more careful. That doesn't matter, but you have to be consistent with your coordinate system. Just don't change your coordinate systems halfway through the problem. That's the big disaster. So the time to reach its high point up the plane, 0.737 seconds. Distance traveled, delta x v naught t plus at squared over q minus 6 times 0.737 plus 7 times 0.737 squared divided by 2 would get us our distance up the plane. Just remembering that that v naught, our initial velocity, is a negative 6 in this coordinate system. With a little bit of luck, I find out that it is a negative 2.2 meters, 2.21 meters. And since we're going up the plane moving in the negative x direction, it is indeed a negative displacement. All right, is everyone okay with these signs? We do have to pay attention to the signs. Okay, now this thing is coming back down. What's the speed at the bottom? And how do we get there? Do you have a way to find it?
You know the distance, you know the acceleration.
You know the distance.
The velocity is 0. Starting to go down.
Set the displacement equal to 0. Find the time. Won't work. Won't work. We don't know the acceleration.
Right.
Friction is throwing it off. You have two different accelerations.
Changes, so you have to calculate the acceleration.
Friction is going down the plane as the mass goes up the plane. Friction is going up the plane when the mass goes down the plane. So you've got two different accelerations. And that's what you got to do. So set it up and see if you can find it. That's what I calculated, yeah. Did anyone else get that acceleration? You got the same for that one? Sure. See if you can calculate the new acceleration. But going down the plane, the friction changes direction.
So basically the same thing, but minus the.
Probably, but that's always kind of an iffy thing to do, to say, oh, going down the plane, I just changed mu to minus mu, and it might all work. Probably does. You know, if you were out of time on a test and you have 5 minutes left, I wouldn't hesitate to just change that time and go for it. But if you have time and you want to make sure you do it right, and NASA's paying you for this, yeah, then you want to get it right. The other reason, does anyone really want to walk through how to find the time and the velocity going down once you have recognized the whole issue that friction is changing direction on you? That's where you have to be so careful. Friction just does cause a lot of issues that way. If not, then I'll just leave that as an exercise. You can work through it during your next class, and we can come back and talk about it. But just be wary that the friction changes direction when it's coming down the plane. Sure. So, we got our mass to the high point on the plane. So there's 2.7 meters up here, right? 2.21 meters. Magnitude 2.21. Okay, now we are wanting to find our normal force. That's not going to change. Our gravitational force actually doesn't change, but our frictional force is now going up the plane, FFK. And we're just assuming that it stops instantaneously and doesn't actually turn into static friction, so I don't have to deal with that question. We'll just deal with this one. And we will now want to, step one, since we know it's going to accelerate back down the plane, we know we have an acceleration in that parallel to the plane. We'll use that coordinate system still. F in is still F in J hat. FG is equal to FG sine theta. And so there's our same three vectors, but now we see that, okay, it is all the same except for friction has changed directions. Summing the J hat forces, we get Fn minus mg Cosine theta is equal to MAY. That's still 0. We still assume that it's not moving perpendicular to the plane. From that, we have Fn is equal to mg cosine theta. Summing the I hat forces, we have mg sine of theta minus mu k mg cosine theta is equal to ax. And again, we get to drop off the masses. There's our acceleration. Our new acceleration down the plane, ax is equal to g minus mu k times the cosine of theta. A little bit of luck, we find out that our acceleration is 6.87. 6.88. The final then is equal to the initial squared plus 2a delta x. It's starting from rest at the top of the plane. 2 times 6.88. And this time it's a positive displacement, 21. And we get 5.51 meters per second in the positive I-hat direction. Any surprises there? Questions? Okay, we need to shift gears a little bit and talk about circular motion. And for the moment, it's going to be a special case of uniform circular motion. So by this we mean our object is going in a circle. And if I want to draw the velocity of the object, I always draw the velocity as tangential to the object. And here's our radius of our circle. And if you pick different points around that circle, you have different velocities. So if I pick another point on the circle, say up here, my velocity is actually the same length. Let's call that V2, we'll call that V1. And the idea of uniform circular motion, the uniform in uniform circular motion is that V2 in magnitude is equal to the magnitude of V1. The speed does not change. So that's what we mean by uniform circular motion. And given those two velocities, I would like to construct delta V. the vector that is v2 minus v1. Let's see if we can graphically construct that. Go ahead and try to find out what delta V looks like from a graph, basically, from this graph. So you're probably thinking that delta V is V2 plus a negative V1. So what does V2 plus a negative V1 look like? Put them head to tail, draw the resultant vector, and see what you come up with. So if I want to consider what negative V1 looks like, looks something like that, negative V1. Draw the line that points from where you started to where you ended, delta V. Not terribly exciting. Do we see the construction? All right, do it again, this time with a smaller delta theta. Change that to a smaller delta and see what your diagram looks like. The idea being, see if you can draw a conclusion as you take delta theta smaller and smaller, what direction does it point in? Towards the center, right. So if we take here V2, that's kind of a nice place for V2 to be. And if I take V1 ever so close to it, it gets a little bit harder to draw. And these two are supposed to have the same length to make this diagram work. And then, of course, we want minus V2, minus V1. And the better you can draw this, the more closely your delta V will point towards the center. Yeah. Moral of the story, the acceleration in the limit as these delta V's get smaller and smaller, acceleration points towards the center of the circle. Towards the center, so that gets a new name. Centripetal acceleration, or center pulling acceleration. Acceleration is pulling towards the center. If we play around with these small changes, we can take a look at the magnitude of the change in velocity. And we can write that delta V over V, which is the percentage change in the velocity in our small delta, is approximately delta L over R. That's supposed to be an L. And that L is the distance that it travels . That would be our delta L. That's our delta theta. This is kind of compelling. Then our acceleration in the limit that delta t goes to 0 of delta v divided by delta t. If you play around with that ever so slightly, you can come up with the limit delta t tends to 0 v delta r over v delta l over r delta t, and in the limit that goes to 0, that term in parentheses becomes a second v. And so our upshot of all of this, it's kind of a plausible way to argue that you get there. In uniform circular motion, our acceleration is v squared over r. We're talking magnitudes here. Here's the magnitude of your acceleration. What direction does your acceleration point in? Towards the center. Is acceleration constant? It changes direction. You got to remember to qualify all your statements in terms of vectors. Magnitude is constant, yes, but the acceleration direction changes. Okay. What goes around the Earth? The moon, you're sure. There was this old French version of Who Wants to Be a Millionaire, where they were asking this poor contestant. Everyone remembers the game Who Wants to Be a Millionaire, right? So they're asking this poor French contestant, you know, it's like really early in the series of questions. What goes around the Earth? And his four choices were like the moon, Venus, and Mars, and the sun, or whatever. Only four choices. And for whatever reason, this guy was not sure. And we just couldn't figure it out. So he said, okay, reduce it by 50%, you know, okay. They take away the sun and Venus, and he's left with the moon and Mars. What goes around the Earth? And he's starting to sweat bullets in this French version of this show. And, okay, so what's after 50% option? You can phone a friend. He didn't have any friends. So they polled the audience. And anyway, so the audience came back with the poll that 75% of the French audience said Mars goes around the Earth. You know, you kind of wonder if maybe the audience in those things isn't exactly sympathetic. Maybe they're future contestants and they want to bump this guy off fast. I don't know. I can't believe the French educational system would be that bad. Anyway, so the moon goes around the Earth. How long does it take? Roughly. Roughly, if you had to guess. 24 hours? The Earth, what goes around the Earth? The moon, right? How long does it take? Right, the moon comes up every night. What's the problem? We're turning, right. It's a month. That's the origin of the month. Right. Because of moving coordinate systems, it's a little bit, it becomes a fishy to actually, what we talk about is the position of the Earth relative, the moon relative to the stars. But anyway, 27.3 days works. And then how far is the Earth from the moon? Far, far away. Okay. If you had to, how would you determine it? Could you determine it?
3 days rocket ride.
3-day rocket ride. The Greeks were able to determine this stuff, and they got it nearly right. So how do you determine these things? Right?
The Greeks had a lot of people.
They did. They did. I mean, there's a lot of politics over exactly how the Greeks were able to figure out all this stuff. I mean, they had a whole society set up for slaves and whatnot, so yes, they were able to do this. But they were able to sit around and do this. One thing that they didn't like actually doing was experiments. But they like to sort of cerebrally think about everything. And they were able to figure out, this one actually is an experiment. But what they figured out is that the Earth's moon distance we'll call it Earth Moon, is approximately 60 times the radius of the Earth. So now, okay, let's figure that out, and that's just about right. How did the Greeks measure the size of the Earth? They were able to do this. This information was lost, by the way, and by the time Columbus was setting sail, the Earth was thought to be considerably smaller. If he had known how big the Earth was, he probably wouldn't have set sail. Nobody would have funded that voyage because it was suicidal at that point. But he did not pack anywhere near enough food and gear to survive on the voyage if he was really trying to make it to India from Europe. He wasn't going to make it. Okay, so the Greeks were able to figure out that the size of the Earth. How did they do that? Walk around it. Not quite. Okay, so you have to have a picture of the sun. We got our nice picture of the sun here. And here's our Earth. And the idea was that at noon on a certain day in a certain city in Greece, it was a well, right? They looked down a well, and the sunlight goes straight down the well. And at the same time, in another city, certain mileage north, they find out that the sunlight makes a shadow on the wall of the well. And they measure the angle of that shadow. And from that and from all the good geometry that they were able to develop, they figured out the radius of the Earth. And what they had done was measure this distance, measure those angles, and work it all out. So that's how they were able to get that. A bit more convoluted exactly how they get the size of the moon, or the distance of the moon from us. How do we even know the shape of the moon? Well, when you look at it, it's kind of round, right? But maybe it's a cylinder, or looking at it on an edge. Things like that. How do we know that the Earth is round? So the Greeks had time to think about all these things. The shadow of the Earth on the moon, also known as the eclipse, right? From these kind of ideas, they were able to figure out a lot of this stuff. Radius of the Earth. See if I can remember what it is. Yeah, a lot of natural, all of physics used to, in many older schools, was called the Department of Natural Philosophy. 6,380 kilometers. Watch out when you're dealing with astronomical distances, because they're not SI units. You're dealing with kilometers, you're not in SI units. Be a little bit careful. Okay, we've got the time to go around the moon to go around the Earth. We've got its distance. We would like to be able to figure out its acceleration. This is the radius of the Earth. This is the Earth-Moon distance, 60 times the Earth radius, roughly. So what my desire here is to come up with the acceleration magnitude of the moon. And we know that this is going to be v squared over our Earth-Moon. The Greeks were able to come up with an idea of the Earth-Moon distance. So the denominator is known, 60 times the radius of the Earth, from the point of view of the Greeks. The speed. Could the Greeks have figured out the speed of the moon? Basic ideas about speed. Distance traveled divided by time taken. How far does the moon go in one orbit? Two pi times the radius of the Earth-Moon. 2 pi r is our circumference, right? Divided by the time. Just going to write that as our time. That time happens to be the 27.3 days. Again, not SI units, but a common one. period. What is the period of the motion? Period, but period is, it means the time for one cycle. So the period of the Earth around the moon, of the moon around the Earth, 27.3 days. Putting all that together, let's calculate the acceleration of the moon. You see, the Greeks knew all this about the moon, but they didn't calculate the acceleration of the moon because they thought the moon was in perfect motion and it wasn't being accelerated. It was Newton who came along and said, the moon's accelerating. All right. Acceleration in SI units. It's going to be 2 pi times 60 times the radius of the Earth, 6,300 and, what did I say, 78? 87 or 78? 80. This will be the velocity divided by 27.3. How do I go from days to seconds? That works. 24 is a bit of an approximation, but we'll take it. It's almost 24 hours in a day. Times 3,600 seconds in an hour. So there's our velocity. And then, of course, our acceleration is going to be v squared over r. Let's see what that velocity comes out to be. I'm coming up with about 17 meters per second. No, I missed the 60 there. 60,000. And our acceleration 0.0027 roughly meters per second squared in SI units. Questions? All right, let's take a short break, get some air, stretch your legs. Come back in about 15 minutes. We're going to do some more lecturing today, then Thursday we'll do some lab. Anyone have questions about the exam that they wanted to discuss? Now would be a good time. Can you retake it? Yeah. I'm sure. I'll get one. I'll bring it in. That's fine. For days for? Yeah. Right there. Yeah. All right.
I just want to say one thing. I'm here, I just cannot go. So the answer here,
Yeah, I was wondering how you did that.
Yeah, I did here, but I just want to give you the clear answer. So I just got it here, but I can't here.
Oh, okay, yeah.
You want to give me some more?
Yeah, I'll give you those. It's you were trying to communicate. I appreciate that.
This part still confuses me about which quadrant. So how would I figure that out? This one kind of seems to be.
Okay, so again, our velocity is up here.
Right.
This is minus 7, minus 13. Minus 7.
Alright, so what do I do when I just use argument and I use the y-max, I got like
Exactly.
63
And
61.7.
And the problem
So the
is,
calculator always gives it in quadrant 1 and 2, is that correct?
1 and 4.
Or 1 and 4, yeah.
So you should have recognized that that's not that angle.
Uh-huh.
So you just need to, because it's over here, you just take that and add 100. Yeah.
And then I would just write that angle and say in quadrant 3, do I have to specify that? Or if I just write that angle?
Well, you should communicate that you know that you're pointing at quadrant 3 relative to
Quadrant 3 and then write
it's 200 and whatever it is.
okay. And then if I were to just leave it in this form, I would just say it's 61.7. I got one problem with the constant.
But it's not.
Right.
If you wanted to do that, you could say, well,
It's not the actual.
you could say this one is 61, but then you have
Below the negative.
below the negative, then it's
Almost. Yeah, okay, no, I
yeah. Let me write that down. Let me go back to you. What's going on?
John A. I got one in this one. I go for B.
So they calculated the concentration and you averaged them. That's not true. The change in the velocity divided by the delta V. The definition of average acceleration. So in this case, V at 18. Yes, because what's going on is not clear. You should be able to spend the time and make sure that your math is correct. I'm not going to give you anything.
I'm just wondering what you mean by this, because you said that's right, and I don't.
So this is the displacement, the average acceleration. You have the right expression. So you have something that's going on in the evaluation. Because your accelerated expression is correct, but that's not correct. So check your evaluation. These two includes.
Then I actually like big problems to deal with. I think like weird that is like these like you play with C and then they have like equal.
I watched like for Dolly Father, but they need to study the ladder. I think you most of them something that we're not. I watched Here Comes the Boom and I don't know if I know if this it is. It's kind of weird when actually when you talk about I'm supposed to tell them about how much I messed up on that value. And once it ever I messed up. That's where I thought you doesn't know. Yeah, this is not really hard. I was able to get my largest tax right. Actually, that's weird. That for example, the first second question because I didn't read. I don't know my just for that, that's just one.
Yeah, I got one of them wrong. I saw it, I'm like, no, it's wrong. I started looking at people. Why did I do this?
And then the last thing I displacement, like my displacement, I was going to take out or not. I was like, okay, what do you minus the and then divide it by but I was quite a fun.
Well, I think if you say that, if I get like really good grades, that's not you have to you have to have a function everything with you. So what? So that's the thing to have. You have a resolution you have to have a quality stand. Like the lowest of the yeah. I mean, basically, drop one. Like, yeah, basically, if you have a good grade telling them it's fine, you can just keep that grade. Yeah, if you're okay with a B, you can just not take it. If you're okay with a B, you can not take it. So it's not really the best thing to do. He just drops one exam and the final is say like any other exam. Like, yeah, that's 10%. Yeah.
Oh, that was my I understood it. I thought you said it has to have like an average of all the exams in order for you to not be higher than
well, that's the smartest. If you have an A before the test and you take the final, you can't go any higher.
Yeah, or you could potentially go at 10%.
No, not really. You drop something.
You drop something. You don't fully adjust this one for I get it. So it's 20%, 20%, 20%. So it's like after that, one is a fourth question will also partially get out. And the APA have really high scores. They're going to drop down and it's going to be the highest. So it's going to be a the other one, another one today, that one you can get right with it.
Yeah, I think it's fine. But if your grade is low,
that's also kind of
you don't have any the final, you can probably take it. You can't. Exactly. Yeah.
Unless you have a, if you have a decent grade, if you have a decent grade, then you have a low grade on one thing. Well, you have to actually do a weighted average to figure that out. That's the
Basically, you can't really base your grade on that. Only like a 7, you might get an A or like a high. Right.
If you have 10% of the final.
Yeah.
you have to have a high, you have to have a high.
Oh, yeah.
Like regardless, even if you don't have an A or a B or whatever, like you can't lower your grade with the final. Unless you already
Because I was like, I understood that he said,
and the final is not a final.
but I thought that he said you have to have an average A in all the exams. But that's how you don't have to have.
That's kind of what's in my college.
Why are you letting it here?
Why not?
It's not like you fail the final.
But some places were, there were some classes that were like, where it's like,
Yeah.
You have to pass the final by something.
What is the thing that there's no like a all content, but it's just like opinion. It's not a special test.
It's not like 20% of the grade.
You can get one wrong, you get an examination before that.
I'm like, starting to get a second, you can
do it in order to like understand how why you correct you and I can do it. I think I honestly thought I wasn't going to do that, honestly. And then I just do
I did like the first one and I did the first one I did, I really did. I did like all the homework, like all the way like in a row. Or anywhere. So math, so just like watch the video and change the numbers and that's it. Press enter.
And that's 7.7 is like, has like 5 questions, and then I have like tables and like shapes that are like, what the hell is this?
That's already 7.7.
Yeah, that's she told us to finish up the site. So, yeah, say 45. I just wish that you would run up the swing.
I thought
I remember really like this is a nice thing to do, like short and then I can make I would have got in like a high speed, that's how I was something that I was confused with the Galatians. So by the
I got confused on that last question. I sat there for like 10 minutes, kind of like, and then my nose was like, oh yeah, this is it.
The last question is an easy question, but when I got to the question, I was like confused, explaining, so I just like made it so easy for myself.
Well, mine was it's stupid because all the other questions
Oh, no.
were good. In the very first question, I forgot.
Okay, but I didn't tell you where the high is.
Was there 2?
Yeah, it was 96, 94. Well, they might have been 2 with 96. There's like no history of colors.
Yeah. Well, did you do a Partlan PHYS?
Basically, it was 2 points for each thing. except you need units there. So you got those two, those are both wrong. You got 1 point for that.
So 4 and 5?
2, 2, and 1.
Oh, okay. So you said 2 points for each, right?
Yeah.
So then 6.
6, except you need units.
You mean mirror?
There was some other issue.
Yeah, these two are wrong because I didn't change it. Isn't this one right?
Let me take a look at it after class. Okay.
Okay.
We'll do it then. All right. Period 2 pi r over v. Units of time, right? V is equal to A is equal to V squared over R. What I want you to do is a little bit of algebra and come up with acceleration as a function of period. So just go ahead and do that algebra and determine that functional dependence of acceleration so that if you know the period, you can come up with the acceleration. Okay, so we take the first equation, solve for v, plug it into the acceleration, and then you're done. Go for it, see what you get. Time. Period as units of time. So you got V is 2 pi r over t. We're plugging that in there. We'll find out that A is equal to 2 pi r over t, but you've got to square that, divide by r. So we get 4 pi squared r squared over t squared r. One of those r's disappears. There's our acceleration, 4 pi squared r over t squared. Centripetal force. F is equal to ma, which is equal to mv squared over r. This comes up over and over again in different places. So you're going to run into it in 260 and again in 270. It comes up a lot. Questions? All right. Let's take a more practical case. Ferris wheel type of ride, you can imagine. Has a rather large radius. And let's see. But it makes one cycle in 30 seconds. Therefore, I told you the period. I told you its radius is 20 meters. You can tell me what its speed is, right? Assuming that it doesn't stop, it just keeps going and going. What's the speed of the object for this Ferris wheel ride? Two pi r is the circumference divided by 30 seconds. And we get 4.2 meters per second, roughly. Now, I hope everyone has had an opportunity at some point in their life to be on a Ferris wheel, so that you have some idea of what we're talking about here. I mean, everybody's been on an elevator, but Ferris wheels, maybe not. Okay, so you're seated at the top of this Ferris wheel, enjoying yourself, looking out at the view of the city. And you're moving at the same time. And the idea is, what is your apparent weight at the top of the Ferris wheel? We're also going to do this at the bottom, but let's see if we can figure out what our apparent weight is. And the idea of this weight is just the normal force. The normal force provided by the seat. What is that normal force provided by the seat? See if you can come up with a way of dealing with this way. Sum your forces, see what you come up with. Oh, we need a mass. So our mass of our person will be 80 kilograms. That's the speed of the person at the top, yes. 80 kilogram mass. What's the apparent weight? So you want to do a free body diagram and identify your forces acting on this body. So here's our person. There's clearly the normal force acting up. And there's clearly the gravitational force acting down. Any other forces in the picture? Where's velocity? What about force? Adrian.
What about the acceleration
The centripetal acceleration and the centripetal force. What about it? It does point down. But these are the only two forces acting on this body. That centripetal force is the result of these two forces, which is what you have to keep in mind. So these are the only two forces. There is the speed acting up and there is gravity acting down. The result of these two is our centripetal acceleration. We'll call it FC. Is there an acceleration in this problem? Do we know which way it's pointing? It seems to have already agreed that it's pointing towards the center. And this is my particular flavor on this, is you know the acceleration that predicts, that gives you the best coordinate system. So since we know the acceleration is pointing down at this point at the top, Then I want to work in a coordinate system where I hat points down. The acceleration gives you your coordinate system. And in that coordinate system, we have f in vector is equal to minus f in I hat, and fg is equal to minus is equal to plus mg I hat. And our centripetal centripetal force is mv squared over r in the I hat direction. And remembering that that latter one is the result, we have summing our forces, we get minus f in plus mg is equal to mv squared over r. But this game sort of helps you keep all the directions correct. Solving for f in, we get f in is equal to m times g minus v squared over r. That's what I got. Is that what you got? All right. Now you see how to make the Ferris wheel more fun, right? What can the normal force do? The normal force, which is the seat on the ride, can only lift up, it can't pull down. Of course, they do put seat belts on it, safety bar. But you can make this Ferris wheel go faster until the person has to be held down by safety bars and whatnot. Yeah, it's a fun ride. So the normal force is less than the normal force would be if the person was just standing still. And this has to do with the rotational motion of the Ferris wheel itself. The normal force at the bottom of the Ferris wheel ride. You were able to set up that equation and get it right? This is the normal force at the top. What is F in at the bottom?
Basically, it would be the same thing, but with different signs, because if you set acceleration going upwards in this case, it's because it's pointing toward the center.
Mm-hmm.
You make the force Fn part of it.
And you just hope it all works out. So here's your normal force. Here's your acceleration towards the center. Gravity is still pointing down. So because of acceleration pointing towards the center of the circle, I'm going to choose my positive direction to be in that direction. And when I write my forces then, Fn is equal to plus Fn I hat. And Fg is minus Mg I hat. Summing the forces that are acting on this thing, I get Fn minus Mg is equal to Mv squared over R. My centripetal force is pointing towards the center of the circle. That's making me go in the circle. So solving for Fn, this is at the bottom. We get M times V squared over R plus G. All works out nicely. Questions on the process? Yeah. Sure. Higher? 4? That one? You want to see more? Okay, in the case of Ferris wheels, we have a normal force. And then we have devices like this. Yeah, won't hit anybody with this. There's no normal force in this picture. So what forces do you see acting on this little mass? The tension and gravity. Now there is some minimum speed which width will be made here, right? There. I need you to find that minimum speed. Almost the same as this, except you got tension forces instead of normal forces. See if you can set it up. Find the minimum speed and put that need to rotate this thing in order for the tension to not go to 0. In this case, the tension is a positive number pointing towards the center. The tension can't be a negative number because it's just a string. Oh, okay, we'll just leave it as an expression. Yeah, we need a mass and a radius, but we have those as symbols. See if you can come up with an expression for your minimum velocity. So hopefully you set up an equation that looks like P plus mg is equal to mv squared over r. Our tension is pointing towards the center of the circle. Our force of gravity is pointing down. Our acceleration is also towards the center of the circle. So that would have told you that everything is pointing in the positive direction. Now the question is the tension. And for our string, since it's not a solid object, our tension minimum is 0. We can't have a negative tension. Therefore, if I put in our minimum tension, we get mg is equal to mv min over r. And of course, it's nice that the masses drop out. V min is equal to g times r inside a square root. Will not move in a circle if I go less than that. I would have to have some kind of negative tension to make it go in a circle. So no, we don't need the mass. Apparently not. Yeah.
We need the normal force.
There is no normal force in this picture.
The tension opposed to the normal
The tension in this problem is similar to the normal force in the previous problem.
We only need normal force if we're sitting on top of the object.
If there's a surface, correct. Okay, there's more that we do with this. Of course there's more. So we got a mass on a string, and I'm going to make it go in a circle, but a different circle. This one is a little harder to visualize. Well, we're going to assume that it's a perfect circle. Where is that circle? In a plane parallel to the floor, correct? All right. Can you visualize the radius of that circle? Okay. Can you visualize the cone? Can you make a diagram of that cone? And the cone angle is the half angle. And this device is called the conical pendulum because it has a regular period every 2 seconds. It's repeating itself, right? So it's called the conical pendulum, and we want to see if we can analyze these forces. See what you can come up with about the conical pendulum. How do you diagram that? Start with a diagram and see if you can do some analysis. Not always they give you a picture. Sometimes they just tell you a description. You just saw it. We had the description. You should be able to come up with some kind of diagram and make an analysis. There's a cone. There's a radius the length from the apex of the cone down to the plane in which the cone is in. There's an angle, the half angle of the cone at the apex. There's actually the radius of the circle that the mass is singing in, the horizontal radius that you have to pay attention to. Trig there. And if possible, what I'd like to come up with is a prediction for the period of this cone, conical pendulum. So step one, if you can get past that, then the rest of the section up there, the three-body diagram, your vectors in the coordinate system. Is there an acceleration in that picture? If so, in which direction does it point? Depends on how you set it up. You could choose different, you could have different diagrams, but you should all end up with the same ideas. Acceleration is towards the center of the circle. So that would seem to say, let's take a coordinate system if you have a diagram similar to mine, that would be the I-hat direction and that would be the J-hat direction. We're going to need to analyze the forces in terms of those directions. So we need to first label them in our diagram. There's my tension. And there's my gravitational force vector. Breaking my tension vector up into two components, horizontal and vertical. Horizontal one being related to the cosine of the, sine angle, right? Cosine of theta. A gravitational force vector minus mg j hat. Did we get that far? Did we agree on which dimension? I thought we erased it and wrote what I had there, didn't I? Okay. One of those. One of those. Alternate interior angles, that must be sine and cosine. And of course, both components are positive. How do you set that up in this coordinate system? That's fine. Summing the j-hats. We have t cosine theta minus mg is equal to 0. No acceleration in the vertical direction. Therefore, we have t is equal to mg divided by the cosine of theta. Next step, we want to sum the I-hat direction. So we have just t sine theta equals ma, x in this case, horizontal. Putting in what we have already, we have, this is mg sine theta over the cosine of theta is equal to m v squared over r, the radius of the circle. Not the length of the string, but the radius of the circle. And of course, sine theta over cos theta is tangent theta, therefore. Then we can divide by the m's. All masses make the same motion. We get v squared is equal to rg tangent theta. So far, so good. You came up with something similar to that? But I want the period. So given what you got here, give me the period. And look here, the mass doesn't matter. We'll make the length about 1 meter. And we'll do about a 10-degree angle. So theta is 10 degrees, length is about 1 meter. What do you predict for the period? Well, you're saying, like most physicists, you're just watching it. The period's about 2.5 seconds, right? Does your prediction come up with about a 2.5 second period? Most theoreticians have no trouble naming the prediction when the experiment was done ahead of time. They always have a hard time coming up with the predictions before the experiment is done. So I've done the experiment for you, you're the theoretician, we should be able to nail it. Length is about 1 meter, angle is about 10 degrees. L is 1 meter. Put things together and see if you can come up with the period. Of course, it would help if you remember what the definition of the period is for an object in circular motion. 2 pi r over v, 2 pi r, the circumference that it travels, divided by the v. That would be 2 pi r over rg tangent theta, side of square root. Helps to rewrite that as 4 pi squared r squared rg tan theta inside of square root. Now we got to go back and figure out what r is.
Wait, I'm trying to center there.
Sure.
Square the top and then put the couple of them.
Yeah, just sort of, it'll help us put things together. So sine of theta is r over L. Why I wanted to do that in the first place was to get rid of those, so I just have 1 r in the numerator. 4 pi squared times L sine of theta divided by g tangent theta. Then of course sine theta over tangent theta must be cosine theta. That's squared, that's all inside the square root. Oh, we get 4. Well, I was Right, so when I brought it inside the square root, I have an r in the denominator, but I have an r squared in the numerator. So cancel it out. Got to be careful about that stuff. So 10. 8. Period. I get a period about 1.99 seconds. Not bad. Questions on the process? Everybody's happy with that? So any thoughts about centripetal force, centripetal acceleration? Concerns with it? As you can see, we've done it in sort of in the vertical plane with the things going around the circle, and then we did it in 2 dimensions with the conical pendulum system. Because now we're getting ready to move this into what's probably its most difficult application. Time for one cycle. Time for one cycle is period. What are units of period? Revolution. Revolution is not a time. Revolution per minute is not a time. We need a time. Second hour day. So period, the units of period, SI unit of period is the second. There's another SI unit of period, the reciprocal of the period is what sometimes gets talked about. 1 over the period is called the frequency. And this is measured in hertz in the SI units. SI unit of frequency is hertz, not the car company. This is also written as seconds inverse. Or it's also written as 1 over seconds. Frequency is the number of cycles per second. Now there's more language to this. There's a language of revolutions. How do we go from cycles per second to revolutions per second? One cycle is 1 revolution per second, which is equal to 2 pi radians per second. Angular measure. We're going to come back to that later on. Okay. Friction yet again. See if we can get to the most difficult case in the next 20 minutes. We've got a car going around the track. So this is the top view. Not a very good track, right? There's my car, and it's going around the track. And we need a side view of this thing. So here's the center of the track, there's the center of the track, here's the track, and here's the car. The tail lights of the car. The car is moving into the page. And how is the car able to go around the track? And don't say because the driver turns the wheels, right? What? The friction. We need friction. Friction with the road. And if you've lived where there's ice, certainly not in California, but if you live where there's ice and you try to go around a curve on an icy road, you find out you can turn the wheel any way you want and you're not turning. It's more fun, yeah. So there's friction in this picture. And can you see where the friction is? Where is the friction? The tires. Where are the tires? Opposite the direction of motion. That sounds like a good guess, is it? Here's your tire. That's why I have these things sitting around here. The tire's moving like that. Where is friction? Friction has to be going that way to get the car to go around the curve. Now, is it static or kinetic friction? After all, the wheel's moving, right?
But it's not moving in that direction.
Not moving in that direction, so that's a good question. And if you ever are in a traffic jam where you're crawling along at like 2 miles an hour, you might stare at the wheels in the car next to you and focus on the point that's making contact with the pavement. And you realize, wow, that point's not moving. The point on the tire in contact with the road is static. So we're dealing with static friction in this case. And of course, static friction when it comes to car tires is simply no fun, right? You want to do all that drifting and whatnot. Okay, so we now have friction going in this direction. And it's a static friction, so I will specify mu s. We are given some static friction and some radius of curvature. This is a flat curve. Pretty soon we're going to put this on an incline, as Caltrans does. There's a maximum speed with which you can make it around this curve without losing control. And we're looking for that maximum speed. And of course, the maximum here has to do something with mu s being related to the maximum static friction force. So see if we can determine the parameters that dictate the maximum speed. Free body diagram, normal forces, find your acceleration, get your coordinate system. Generalized description, it's your free body diagram, your vector forces and coordinate systems, sum your forces and mass times acceleration, determine V max. That's the maximum force of static friction that shows up there, and therefore we have V max, maximum speed for which friction will still get us around that curve. Notice the nice thing about this, the masses drop out. You don't need to know the mass. So V max is equal to mu S RG inside a square root. Questions on the process? Process being more important than the particular result in this case. The flavor here is these three steps. Identifying your forces and your chord well. Step one, the hardest step, getting your free body diagram, getting your forces, choosing the coordinate system. It's usually the hardest step. After that, it's almost a turn the crank sort of thing. Okay, next we would like to be able to get around this track without friction. How is that possible? We bank the curve. So the top view looks pretty much the same, but the side view looks different. I'm going to draw it like so. Here's your inclined plane. Here's our car. And it's going around this track at an angle theta. And here is the center of the circle.
Basically, there is friction going forward, but not.
No, there's no friction in this case. Mu is now equal to 0. It's either going in or coming out. It doesn't really matter for this one. I prefer to think of this going into the page. Yeah, it's going like that. Most cases in California, Caltrans has banked the curves appropriately. There are at least two I know of where they're banked the other direction. There's one on the East Bay, Vallejo, just outside of Vallejo. You come down that long hill, there's a turnoff into the city of Vallejo, and there just wasn't physical space for them to bank that curve properly, so they got fines all over that place warning the truck drivers to slow down and go really, really slow. I forget where the other one was, but I noticed it. I think it was down in Redwood City someplace. Anyway, here's the hard part. Is there an acceleration in the system? It's going around the circle, so the answer is yes. Which direction is that acceleration pointing in? Okay, the acceleration is towards the center. Remember that that is your best indication of the best coordinate system to work in. So in spite of the fact that we have an inclined plane there, we are going to use the regular coordinate system. And this is going to change everything. So we have an acceleration pointing towards the center of the circle. You don't like change. So we are going to choose our coordinate systems in the more typical sense, I hat, J hat. So we've got our coordinate system, and now we need our forces. Here's our normal force. Here's our gravitational force. And we don't have a frictional force because mu is 0. So FG works out to be minus mg j hat. That's all cool. Fn, however, you're going to have to do some more work on this one. Because now what you're doing is breaking the moment force vector down into components. Parallel and perpendicular. You're trying to decompose this vector into parts that are going in this direction and that direction. This is where drawing flat angles is generally a help, because it's obvious which angle is which, yeah? Relatively obvious. This must be our angle theta. So our horizontal component is related to the sine of theta. And our vertical component is the cosine of theta. And they're both positive. That normal force is going up and through the left. We got our forces. So now we do the sum of the forces in the j hat direction. This time we get F in cosine theta minus mg is equal to 0, or our Fn is equal to mg divided by cosine of theta. Not at all what it was before, because we have a different coordinate system. Summing our I hat coordinate forces, rather, we've got Fn sine theta mv squared over r, because we know we're going in centripetal acceleration force. Masses disappear. We get V is equal to Rg tangent theta. This is the only speed at which you can make it around this track. You don't have a choice. So what happens if you go too fast? What happens if you go too slow? Where's my curve? There's my track. If you go too slow, you slide down the track. And if you go too fast, you slide up the track. But if you go just exactly at that speed, you will go in a circle around that track.
So that's just that when you're going exactly at that speed is when your mu is equal to 0, but if you're going at a different speed.
Well, mu is 0 everywhere on this one because I decided to make this one the icy track. And so the next challenge, let's see if we can get through there, is to put friction into this picture. And then you've got about the worst problem, at least for a couple of weeks, that we come up with. Okay, let's add in some friction. Add in our static friction. And in particular, I want you to find V min. So now with static friction, so mu is not 0, there is a minimum velocity. And if you remember which way you wanted to slide without friction, if you went too slow, that tells you which direction friction is acting in. So if you go too slow, friction is acting up the plane. If you go too fast, friction is acting down the plane. So just repeat that whole exercise with one more force vector added in there, the friction force. So you're decomposing your static friction vector into those two pieces, parallel and perpendicular. I came up with cosine for the I hat and negative cosine for the I hat and a positive sine for the J hat. Do you agree? You don't want to. Because we know what direction the acceleration is. And if you work in a different coordinate system, then your acceleration will have two components, which will give you a lot more algebra later on. But yes, if you want to, drive forth, solve this system using the coordinate system set up on the plane, and go for it. You should come up with the same answer. It's just a lot more work. All right, so we had our normal force from before. Fn was Fn. That was sine of theta, I believe. I hat plus cosine theta. J hat. Breaking that up into those two pieces. Sine plus sine. And we have our Fg minus Mg. J hat. Friction, normal force, gravitational force, we go for it. Sum the J hat components. The magnitude of our static frictional force times the sine of angle times our normal force cosine of that angle minus mg. You can play a little bit of a game. You have to remember that this FFS, that's the magnitude. Our game here is that this is mu s Fn. So we'll want to replace that with the other one. So we've got mu s Fn sine of theta plus f theta. Now we sum our I hat coordinate, our forces rather. We have two. We have a static friction component, and we have a normal force component. Fn sine theta. And for our friction, that was a negative. Cosine theta. And this is equal to mv squared over r. Okay. Solve this for Fn, plug it into there, you're home free. Looks terrible. So here's where this trick comes up that'll save lots of algebra time and potential mistakes. We're looking for the velocity, so let's do it this way. We're going to rewrite this equation as taking the second one, Fn, we factor that out. Sine of theta minus mu s cosine theta equals mv squared over r. And we're going to divide everything. We're going to rearrange the equation above that. Take this one, factor out the Fn, move the mg to the other side, and we'll do a division by that. And we get f in sine of theta, there's a mu s there. So it's cosine theta plus mu s sine of theta. And this is mg. And that makes your algebra go away pretty fast. We get V, and this is V min. G times R times nothing nice. All of that goes to that. So that little trick of setting us that rational expression helps the algebra considerably. And when you don't have anything else to do, figure out what Vmax is. In your spare time. Right. And if you think, well, maybe I can just change mu to minus mu, you would be right, it works. In this one case, well, that's probably a good thing to do. All right. Almost done with chapter 5. That's almost the last thing in chapter 5. Next thing we have in chapter 5 are what's called velocity-dependent forces. So an object falling through air where we don't ignore air resistance anymore. We're going to do that on Thursday, and we'll probably do a lab, and I will try to get lab reports out the next, but I don't have my computer yet. I'm hoping to get it back in the next couple of hours, and we'll see if I can generate anything. All right, see you on Thursday.
Some of the labs are graded already?
No, I'm working on the first lab, so we're going to discuss it on Thursday. I don't have any way to record it. Thursday, yeah.
I think it would be pretty down to the simplest possible first, and realizing what the force are.
Copies will have from last month.
Oh, somebody else is asking. Yeah, I think
What are you guys using? Uno también lo hizo completamente.
No, there's not something you can see that. Just don't sit on that on that. Yeah. I didn't really see it in there. Okay, so that's all you're doing. And for this one, usually 1 month is yeah, I mean, you got to the derivatives. But you didn't obviously you didn't plus on the derivatives.
Yeah, there's that really nice to see the regulation that's not.
Like this one, I don't know.
Like, I remember, like, you use the value of A times B, but video coding is over to B times B. And I thought that we don't have to add the two I head and J head.
Oh, I got to ignore them to how to do it.
You did for the subject.
For that product, yeah. That one, that's just one, sure. When I get my computer back, I'll update it, so I'll let you know when you do it.
Oh, yeah. Same with this one, I don't know why, but.
See, you prove the concept in maximum height to find the distance. But you know, that doesn't even engage it. I mean, you can't even use that. You don't really anyway.
I can't use this.
But determine the time in the air and the position equation, and you can't get there from that information. You just apply that max voltage, you don't know. Max height is not an option in this problem. Just like you can't use it under maximum height.
And so for this one, you write the equation, right?
No, I want a description of how you get there.
Oh.
You know, how would you instruct somebody to calculate it without giving them an equation? How do you instruct? What is the concept you're using?
So just tell them how to set fire.
Yeah, you would say you're going to use the horizontal velocity, you're going to determine the horizontal velocity from the given information because you know that there's no horizontal acceleration. From that will give you the horizontal velocity and then work your way from there. That's what you're supposed to do. Now, obviously, you did it because that's how you got yourself there. Because then you build it up in the way it is. But you just need to eventually figure out.
I told you like to find the extra.
But that's not work.
It's not fair. It just seems 6 points for description and only 4 points for calculation. It's not fair.
It's really fair.
I mean, it's like 4 or 5. Like 2 and 5.
You only have to do it 10 times every semester. That's already number 2.
But this one is really hard.
That's why I want you to do it. Because it is really hard. That's why I want you to learn to put your emphasis in, learn how to do that. Because that's what
I mean,
you
like sometimes they have in the mind first time to
I feel like we can make time for doing this.
That's why we're going to 20 minutes.
I think you give us like a 15 minutes.
We can put it
So I do this first, and I have really less time to do this. That's why I really. Yeah, I couldn't finish this one.
20 minutes to do the whole problem.
and it's more sense, so we need more sense, right? Yeah, but it's an opinion to do it. So that's
Thank you.
You're welcome. Yep.